Alright, everyone. We're going to continue from where we abruptly left off, which was in chapter Quantum Magician. Oh god, this section. This was page 190, I believe. Alright. I'll start like a paragraph before where I stopped last time. And besides, last time that was because of low battery, so I apologize for that. Alright. Get your hands off the puzzle. Alright. Let's go. So let's start at the... Actually, let's start at the break. This is a good place. In June 1925, a little more than a month after returning from Copenhagen, Heisenberg was miserable in Göttingen. He was struggling to make headway in calculating the intensities of the spectral lines of hydrogen, and admitted as much in a letter to his parents. He complained that everyone here is doing something different, and no one anything worthwhile. A very severe attack of hay fever contributed to his low spirits. I couldn't see from my eyes, I just was in a terrible state, Heisenberg said later. Unable to cope, he had to get away, and the sympathetic Born granted him a 2-week holiday. On Sunday, the 7th of June, Heisenberg caught the night train to the port of Cuxhaven on the coast. Arriving early in the morning, tired and hungry, Heisenberg went in search of breakfast at an inn and boarded a ferry to the island of Helgoland, an isolated barren rock in the North Sea. Originally owned by the British until it was traded for Zanzibar in 1890, Helgoland was 30 miles from the German mainland and less than a square mile in size. It was here that Heisenberg hoped to find relief amidst the bracing, pollen-free sea air. On my arrival, I must have looked quite a sight with my swollen face. In any case, my landlady took one look at me, concluded that I had been in a fight, and promised to nurse me through the after effects, Heisenberg recalled when he was 70. The guest house was high on the southern edge of the distinctive island carved out of red sandstone rock. From the balcony of his second-floor room, Heisenberg had a wonderful view of the village below, the beach, and the dark Bruden Sea beyond. In the days that followed, he had time to think about Bohr's remark that part of infinity seems to lie within the grasp of those who look across the sea. It was in such reflective mood that he relaxed by reading Goethe, taking daily walks around the small resort, and swimming. Soon he was feeling much better. With little to distract him, Heisenberg's thoughts turned once more to problems of atomic physics, but here on Helgoland, he felt none of the anxiety that had recently plagued him. Relaxed and carefree, he quickly jettisoned the mathematical ballast that he had brought from Göttingen as he tried to solve the riddle of the intensities of the spectral lines. In his quest for a new mechanics for the quantized world of the atom, Heisenberg concentrated on the frequencies and relative intensities of one of the spectral lines produced when an electron instantaneously jumped from one energy level to another. He had no other choice. It was the only available data about what was happening inside an atom. Despite the imagery conjured up by all the talk of quantum jumps and leaps, an electron did not jump through space as it moved between energy levels like a boy jumping off a wall onto the pavement below. It was simply in one place, and an instant later it popped up in another without being anywhere in between. Heisenberg accepted that all observables, or anything connected with them, were associated with the mystery and magic of the quantum jump of an electron between two energy levels. Lost forever was the picturesque miniature solar system in which each electron orbited a nuclear sun. Let me drink some chicken soup. I hope that added to the ASMR vibe. On the pollen-free haven of Helgoland, Heisenberg devised a method of bookkeeping to track all possible electron jumps or transitions that could occur between the different energy levels of hydrogen. The only way he could think of recording such observable quantities associated with a unique pair of energy levels was to use an array. And here, of course, is the array V11, V12, V13, V14, dot dot dot, V1n, V21, V22, V23, V24, dot dot dot, V2n, V31, V32, V33, V34, dot dot dot, V3n, V41, V42, V43, V44, dot dot dot, V4n, and then dot dot dot, VM1, VM2, VM3, VM4, dot dot dot, VMN. This was the array for the entire set of possible frequencies of the spectral lines that could theoretically be emitted by an electron when it jumps between two different energy levels. If an electron quantum jumps from the energy level E2 to the lower energy level E1, a spectral line is emitted with the frequency designated by V21 in the array. The spectral line of frequency V12 would only be found in the absorption spectrum, since it is associated with an electron in energy level E1 absorbing a quantum of energy sufficient to jump to energy level E2. A spectral line of frequency VMN would be emitted when an electron jumps between any two levels whose energies are EM and EN, where M is greater than N. Not all the frequencies VMN are exactly observed. For example, measurement of V11 is impossible since it would be the frequency of the spectral line emitted in the transition from energy level E1 to energy level E1, a physical impossibility. The collection of all non-zero frequencies, VMN, will be the lines actually present in the emission spectrum of a particular element. Oh, man. Another array could be formed from the calculation of transition rates between the various energy levels. If the probability of a particular transition, AMN, from energy level EM to EN is high, then the transition is more likely than one with a lower probability. The resulting spectral line with frequency VMN would be more intense than for the less probable transition. Heisenberg realized that the transition probabilities AMN and the frequencies VMN could, after some deft theoretical manipulation, lead to a quantum counterpart for each observable quantity known in Newtonian mechanics, such as position and momentum. Of all things, Heisenberg began by thinking about electrons' orbits. He imagined an atom in which an electron was orbiting the nucleus at a great distance, more like Pluto orbiting the Sun than Mercury. It was to prevent an electron spiraling into the nucleus as it radiated away energy that Bohr had introduced in the concept of stationary orbits. However, in accordance with classical physics, the orbital frequency of an electron in such an exaggerated orbit, the number of complete orbits it makes per second, is equal to the frequency of the radiation it emits. This was no flight or fancy, but a skillful use of the correspondence principle, Bohr's conceptual bridge between the quantum and the classical realms. Heisenberg's hypothetical electron orbit was so large that it was on the border that divided the kingdoms of the quantum and the classical. Here in this borderland, the electron's orbital frequency was equal to the frequency of the radiation it emitted. Heisenberg knew that such an electron in an atom was akin to a hypothetical oscillator that could produce all the frequencies of the spectrum. Max Planck had adopted a similar approach a quarter of a century earlier. However, while Planck had used brute force and ad hoc assumptions to generate a formula that he already knew to be correct, Heisenberg was being guided by the correspondence principle onto the familiar landscape of classical physics. Once it was set into motion, he could calculate properties of the oscillator such as its momentum p, the displacement from its equilibrium position q, and its frequency of oscillation. The spectral line with the frequency VMN would be emitted by one of a range of individual oscillators. Heisenberg knew that once he worked out the physics in this territory where the quantum and the classical met, he could extrapolate to explore the unknown interior of the atom. Late one evening in Helgoland, All the pieces began falling into place. The theory built completely out of observables appeared to reproduce everything, but did it contravene the law of the conservation of energy? If it did, then it would collapse like a house of cards. Excited and nervous as he edged even closer to proving that his theory was both physically and mathematically consistent, the 24-year-old physicist began making simple errors of arithmetic as he checked his calculations. It was almost 3 in the morning before Heisenberg could put down his pen, satisfied that the theory did not violate one of the most fundamental laws of physics. He was elated but troubled. At first, I was deeply alarmed, Heisenberg recalled later. I had the feeling that, through the surface of atomic phenomena, I was looking at a strangely beautiful interior, and felt almost giddy at the thought that I now had to probe this wealth of mathematical structures nature had so generously spread out before me. Sleep was impossible. He was too excited. So as a new day dawned, Heisenberg walked to the southern tip of the island, where for days he had been longing to climb a rock jutting out into the sea. Fueled by the adrenaline of discovery, he climbed it without too much trouble and waited for the sun to rise. Let me drink some more. In the cold light of day, In the cold light of the day, Heisenberg's initial euphoria and optimism faded. His new physics appeared to work only with the help of a strange kind of multiplication, where x times y did not equal y times x. With ordinary numbers, it did not matter in which order they were being multiplied. 4 times 5 gave us exactly the same answer as 5 times 4, that is 20. Mathematics called this property, where the ordering in multiplication is unimportant, commutation. Numbers obey the commutative law of multiplication. So 4 times 5 minus 5 times 4 is always 0. It was a rule of mathematics that every child learned, and Heisenberg was deeply troubled by the discovery. That when he multiplied two arrays together, the answer was always dependent on the order in which they were being multiplied. A times B minus B times A was not always 0. As the meaning of the peculiar multiplication he had been forced to use continued to elude him, on Friday, 19th of June, Heisenberg traveled back to the mainland and headed straight to Hamburg and Wolfgang Pauli. A few hours later, having received words of encouragement from his severest critic, Heisenberg left for Göttingen and the task of refining and writing up what he had discovered. Only 2 days later, expecting to make quick progress, he wrote to Pauli that attempts to fabricate a quantum mechanics advance only slowly. As the days passed, his frustration grew as he failed to apply his new approach to the hydrogen atom. Whatever doubts he harbored, there was one thing Heisenberg was certain about. In any calculation, only relationships between observable quantities, or those that could be measured in principle if not in reality, were permissible. He had given the observability of all quantities in his equations the status of a postulate, and devoted his entire meager efforts to killing off and suitably replacing the concept of the orbital paths that one cannot observe. My own works are at the moment not going especially well, Heisenberg wrote to his father at the end of June. A little more than a week later, he had finished the paper that ushered in a new era of quantum physics. Still uncertain about what he had done and its true significance, Heisenberg sent a copy to Pauli. Apologizing, he asked him to read and return the paper within 2 or 3 days. The reason for the haste was that Heisenberg was due to give a lecture at Cambridge University on the 28th of July. With other commitments, he was unlikely to return to Göttingen until late September and wanted either to complete it in the last days of my presence here or to burn it. Pauli greeted the paper with jubilation. It offered, he wrote to a colleague, a new hope and a renewed enjoyment of life. Although it is not the solution to the riddle, Pauli added, I believe that it is now once again possible to move forward. The man who took those steps in the right direction was Max Born. He had little inkling of what Heisenberg had been doing since returning from the little island in the North Sea. Born was therefore surprised when Heisenberg gave him the paper and requested that he decide whether it was worth publishing or not. Tired by his own exertions, Born put the paper to one side. When a couple of days later he sat down to read it and passed judgment on When a couple of days later he sat down to read it and passed judgment on what Heisenberg had described as a crazy paper, Born was immediately captivated. He realized that Heisenberg was being uncharacteristically hesitant in what he was putting forward. Was the consequence of having to employ a strange multiplication rule? Heisenberg was still groping even at the conclusion of the paper, whether a method to determine quantum mechanical data using relations between observable quantities, such as that proposed here, can be regarded as satisfactory in principle, or whether this method, after all, represents far too rough an approach to the physical problem of constructing a theoretical quantum mechanics, an obviously very involved problem at the moment, can be decided only by a more intensive mathematical investigation of the method which has been very superficially employed here. Heisenberg has a way with words. What was the meaning of the mysterious multiplication law? It was a question that so obsessed Born he could think of little else during the days and nights that followed. He was troubled by the fact that there was something vaguely familiar about it, but he could not pinpoint exactly what. Heisenberg's latest paper, soon to be published, appears rather mystifying, but it is certainly true and profound, Bohr wrote to Einstein, even though he was still unable to explain the origin of this strange multiplication. Praising the young physicists at his institute, especially Heisenberg, Born admitted that merely to keep up with their thoughts demands at times considerable effort on my part. One morning, Bohr suddenly recalled a long-forgotten lecture he had attended as a student and realized that Heisenberg had accidentally stumbled across matrix multiplication, in which x times y does not always equal y times x. On being told that the mystery of his strange multiplication rule had been solved, Heisenberg complained that I do not even know what a matrix is. A matrix is nothing more than an array of numbers placed in a series of rows and columns, just like the arrays that Heisenberg constructed in Helgoland. In the mid-19th century, the British mathematician Arthur Cayley had worked out how to add, subtract, and multiply matrices. If A and B are both matrices, then A times B can yield a different answer from B times A. Just like Heisenberg's array of numbers, matrices do not necessarily commute. Although they were established features of the mathematical landscape, matrices were unfamiliar territory for the theoretical physicists of Heisenberg's generation. Let me drink some more. Oh, man. Yummy chicken soup. Let's go. Once Born had correctly identified the roots of the strange multiplication, He knew that he needed help to turn Heisenberg's original scheme into a coherent theoretical framework that embraced all the multifarious aspects of atomic physics. He knew the perfect man for the job, one well versed in the intricacies of both quantum physics and mathematics. As luck would have it, he too would be in Hanover, where Born was due to attend a meeting of the German Physical Society. Once there, he immediately sought out Wolfgang Pauli. Born asked his former assistant to collaborate with him. "Yes, I know you are fond of tedious and complicated formalisms," came the reply as Pauli refused. He wanted no part in Born's plans. You are only going to spoil Heisenberg's physical ideas by your futile mathematics." Feeling unable to make progress alone, he turned in desperation to one of its students for help. In choosing 22-year-old Pascual Jordan, Born had unwittingly found the perfect collaborator for the task ahead. Entering the Technische Hochschule in Hanover in 1921 with the intention of studying physics, Jordan found the lecturers rather poor and turned instead to mathematics. A year later, he transferred to Göttingen to study physics. However, he rarely attended the lectures because they were too early in the morning, starting at either 7 or 8 a.m. Then he met Born. Under his supervision, Born began to study physics. Jordan began to study physics seriously for the first time. He was not only my teacher, who in my student days introduced me to the wide world of physics, his lectures were a wonderful combination of intellectual clarity and horizon-widening overview, Jordan later said of Born, but he was also, I want to assert, the person who, next to my parents, exerted the deepest, longest-lasting influence on my life. With Born as his guide, Jordan soon began concentrating on problems of atomic structure. Somewhat insecure and with a stutter, he appreciated Born's patience whenever they discussed the latest papers touching on atomic theory. Fortuitously, he had moved to Göttingen in time to attend the Bohr Festspiel, and like Heisenberg, was inspired by the lectures and the discussions that followed. After his doctoral dissertation in 1924, Jordan worked briefly with others before being asked by Born to collaborate with him on an attempt to explain the width of spectral lines. Jordan is exceptionally intelligent and astute and can think far more swiftly and confidently than I, Born wrote to Einstein in July 1925. By then, Jordan had already heard of Heisenberg's latest ideas. Before he left Göttingen at the end of July, Heisenberg gave a talk to a small circle of students and friends about his attempt to construct a quantum mechanics based solely on the relations between observable properties. When Born asked him to collaborate, Jordan jumped at the chance to recast and extend Heisenberg's original ideas into a systematic theory of quantum mechanics. Unknown to Born, as he sent Heisenberg's paper to the journal Zeitschrift für Physik, Jordan was well versed in matrix theory throughout his background in mathematics. Applying these methods to quantum physics, in 2 months, Born and Jordan laid the foundations for a new quantum mechanics that others would call matrix mechanics. Once Born identified Heisenberg's multiplication rule as a rediscovery of matrix multiplication, he quickly found a matrix formula that connected position q and momentum p using an expression that included Planck's constant. PQ minus QP equals IH over 2 omega. And then on parentheses times I, where I is what mathematics call a unit matrix. It allowed the right-hand side of the equation to be written as a matrix. It was from this fundamental equation using the methods of matrix mechanics that all of quantum mechanics was constructed. In the months that followed, Bohr was proud to be the first person to write a physical law in terms of non-commuting symbols. But it was only a guess, and my attempts to prove it failed, he recalled later. Within days of being shown the formula, Jordan came up with the rigorous mechanical derivation. No wonder Born was soon telling Bohr that aside from Heisenberg and Pauli, he considered Jordan to be the most gifted of the younger colleagues. In August, Bohr went on his summer holiday to Switzerland with his family, while Jordan stayed in Göttingen to write up a paper by the end of September for publication. Before it appeared in print, they sent a copy to Heisenberg, who was in Copenhagen at the time. "Here, I got a paper from Born, which I cannot understand at all," Heisenberg said to Bohr as he handed him the paper. "It is full of matrices, and I hardly know what they are." Heisenberg was hardly alone in not being familiar with matrices, but he set about learning the new mathematics with gusto, and mastered enough to begin collaborating with Born and Jordan while still in Copenhagen. Heisenberg returned to Göttingen in the middle of October in time to help with the final version of what became known as the Drei Männer Arbeit, the three-man paper, in which he, Born, and Jordan presented the first logically consistent formulation of quantum mechanics, the long sought-after new physics of the atom. However, there are already reservations being expressed about Heisenberg's initial work. Einstein wrote to Paul Ehrenfest, "In Göttingen they believe it, but I don't." Bohr believed it was a step probably of fundamental importance, but it has not yet been possible to apply the theory to questions of atomic structure. While Heisenberg, Born, and Jordan had been concentrating on developing the theory, Pauli had been busy using the new mechanics to do just that. By early November, while the three-man paper was still being written, he had successfully applied matrix mechanics in a stunning tour de force. Pauli had done for the new physics what Bohr had done for the old quantum theory, reproduced the line spectrum of the hydrogen atom. For Heisenberg to add insult to injury, Pauli had also calculated the Stark effect, the influence of an external electric field on the spectrum. "I myself have been a bit unhappy that I could not succeed in deriving the hydrogen spectrum for the new theory," Heisenberg recalled. Pauli had provided the first concrete vindication of the new quantum mechanics. And there's our last break. There's about 2.5 pages left. Good. I'll drink some more chicken soup. Alright, let's do this thing. Imagine saying, "Let's do this thing," and immediately starting smacking your lips like a motherfucker. Okay. "The Fundamental Equations of Quantum Mechanics," read the title. Born had been in Boston for nearly a month as part of a 5-month lecture tour of the United States, when one December morning he opened his post and received one of the greatest surprises of his scientific life. As he read the paper by one P.A.M. Dirac, a senior research student at Cambridge University, Born realized that everything was perfect in its way. Even more remarkably, Born soon discovered that Dirac had sent his paper to the Proceedings of the Royal Society, containing the nuts and bolts of quantum mechanics, a whole 9 days before the three-man paper was finished. Who was Dirac, and how had he done it? Wondered Born. Paul Adrien Maurice Dirac was 23 years old in 1925. The son of a Swiss French-speaking father, Charles, and an English mother, Florence, he was the second of 3 children. His father was such an overbearing and dominant figure that when he died in 1935, Dirac wrote, "I feel much freer now." It was the trauma of having to remain silent in the presence of his father, a teacher of French, as he grew up, that made Dirac a man of few words. My father made the rule that I should only talk to him in French. He thought it would be good for me to learn French in that way. Since I found that I couldn't express myself in French, it was better for me to stay silent than to talk in English. Dirac's preference for silence, the legacy of a deeply unhappy childhood and adolescence, would become legendary. Although interested in science, in 1918, Dirac acted on his father's advice and enrolled to study electrical engineering at the University of Bristol. 3 years later, despite graduating with a first-class honors degree, he could not find a job as an engineer. With his employment prospects looking bleak as Britain's post-war depression continued, Dirac accepted the offer of free tuition for 2 years to study mathematics back at his old university. He would rather have gone to Cambridge, but the scholarship he had won did not cover all the expenses of studying at the university. However, in 1923, after gaining his mathematics degree and receiving a government grant, he finally arrived in Cambridge as a PhD student. His supervisor was Ralph Fowler, Rutherford's son-in-law. Dirac had a thorough grasp of Einstein's theory of relativity, which had generated a firestorm of publicity around the world in 1919 while he was still an engineering student. But he knew very little about Bohr's decade-old quantum atom. Until his arrival in Cambridge, Dirac always considered atoms as very hypothetical things, hardly worth bothering about. He soon changed his mind and set about making up for lost time. The quiet, secluded life of a budding Cambridge theoretical physicist was tailor-made for the shy and introverted Dirac. Research students were largely left to work alone in either their college rooms or in the library. While others might have struggled with the lack of human contact day after day, Dirac was perfectly happy to be left alone in his room to think. Even on a Sunday, as he relaxed by walking in the Cambridgeshire countryside, Dirac preferred to do it alone. Like Bohr, whom we met for the first time in June 1925, Dirac chose his words, written or spoken, very carefully. If he gave a lecture and was asked to explain a point that had not been understood, Dirac would often repeat word for word what he had said before. Bohr had gone to Cambridge to lecture on the problems of quantum theory, and Dirac had been impressed by the man, but not by his arguments. What I wanted was statements which could be expressed in terms of equations, he said later, and Bohr's work very seldom provided such statements. Heisenberg, on the other hand, arrived from Göttingen to give a lecture having spent months studying just the sort of physics that Dirac would have found stimulating. But he did not hear from Heisenberg, who chose not to mention it as he spoke about atomic spectroscopy. It was Ralph Fowler who alerted Dirac to Heisenberg's work by giving him a proof copy of the German soon-to-be published paper. Heisenberg had been Fowler's house guest during his brief visit and had discussed his latest ideas with his host, who asked for a copy of the paper. When it arrived, Fowler had little time to study it thoroughly, and so passed it on to Dirac, asking him for his opinion. When he first read it in early September, he found it difficult to follow and failed to appreciate what a breakthrough it represented. Then, as 1 week turned into 2, Dirac suddenly realized that the fact that A times B did not equal B times A lay at the very heart of Heisenberg's new approach and provided the key to the whole mystery. Oof. Dirac developed a mathematical theory that also led him to the formula PQ minus QP equals parentheses 1h divided by 2 omega parentheses I by distinguishing between what he called Q numbers and C numbers. Between these quantities that do not commute, AB does not equal BA, and those that do, AB equals BA. Dirac showed that quantum numbers differ from quantum mechanics. Dirac showed that quantum mechanics differs from quantum mechanics. Dirac showed that quantum mechanics differs from classical mechanics in that the variables Q and P, representing the position and momentum of a particle, do not commute with one another but obey the formula that he had found independently of Born, Jourdan, and Heisenberg. In May 1926, he received his PhD with the first ever thesis on the subject of quantum mechanics. By then, physicists were beginning to breathe a little easier after having been confronted by matrix mechanics, which is difficult to use and impossible to visualize, even though it generated the right answers. The Heisenberg-born concepts leave us all breathless and have made a deep impression on all theoretically oriented people, Einstein wrote in March 1926. Instead of dull resignation, there is now a singular tension in us sluggish people. They were roused out of their stupor by an Austrian physicist who had found time while conducting an affair to produce an entirely different version of quantum mechanics that avoided what Einstein called Heisenberg's veritable calculation by magic. And that is the end of chapter 8. And let's see how long the next one is. It is 23 pages. Boy oh boy. Alright, I'm gonna finish my chicken soup, my quantum soup, and then I'm gonna go upstairs. I might do another blog later this evening. Cool. Alright. Okay, see you guys later, y'all.